Thank you.
And we will then go on to the next one, which is also from University of Southern California, Saba Raji. If that was the correct pronunciation.
Saba.
I'm
Saba.
Saba. Yeah, Saba Raji.
Raji.
Good
And you're
morning,
a
Saba.
creative and
Hi,
you're a
everyone.
creative
Hi,
architect
Professor.
and you're a creative architectural designer and building performance and technology student at the School of Architecture with Madhu at the University of Southern California, right?
Yes, so I've
Before
studied.
Saba says something, I want to tell something about this person. Our studio is based in the School of Engineering. Specifically, my home department is the astronautical engineering department, not the aerospace engineering department, but the astronautical engineering department. We are really looking at space and space environments. Once in a while, I get a student from the School of Architecture. Saba's work is in the area of building science, Nicholas. It's a little bit different than architecture, but she holds degrees in architecture and working towards something that marries architecture and engineering. Go for it, Saba.
Yeah. The floor is yours.
Thank you so much. Hello, everyone. Again, my name is Saba, and as a Professor Madhu and Nicholas has introduced me, I'm a student. I'm no expert. I'm just took a class with Professor Madhu. I was really interested in space architecture, and I wanted to kind of explore this direction within the building science and architecture, and that's why I took that. And I've seen a lot of companies within the architecture firms. They have lean towards this direction, which is a very frontier direction, kind of thinking about the future, thinking about human habitation beyond the Earth surface. And that was my interest too, to be able to kind of think about that direction. Within that framework, I'm going to share my screen, first of all. Where's the share button? Oh, there you go. Are you able to see my screen?
Starting to, yeah.
Yes. Okay.
Oh, there we go.
Perfect.
Good.
So today I'm going to present a LEADER Lunar Equatorial Daylight Exploration Rover, which is the mission architecture in support of Artemis 3 lunar landing and beyond. And that's very conceptual, mission operation architecture that started with the framework of space architecture class taught by Professor Madhu. A little bit of overview about the project. So as NASA plans to land crew at the lunar South Pole in Artemis 3 mission in 2026 earliest, several new systems has to be tested and certified before this mission. For example, we are seeing a lot of test operation by SpaceX for Starships and all the launching vehicles. And within the framework of rovers concept, NASA's pressurized rover prototype has been tested by researchers from NASA and Japan Aerospace Exploration Agency. Let me move this over. So from the beginning of the class, there were several questions rose up to kind of develop a concept. The first question was, can we use modular elements of existing space transition assets to create a phased mission architecture for a lunar landing rehearsal in support of Artemis 3 mission. The second question was, how can we integrate a rover into a lander and a lunar habitation to minimize astronauts' transitions between vehicles and enhance safety and efficiency? Basically, how can we contain astronauts without allowing them to continuously come out of the different transition vehicles and exposing them to the harsh environment of outer space and lunar surface? The third question was, are there alternative locations to the lunar South Pole that offers smoother and safer operations in terms of the environment and terrains? So within these base questions, the concept, the very conceptual concept got shaped. The leader Lunar Equatorial Daylight Exploration Rover Traverse Mission concept proposes an alternative to Artemis 3, supporting lunar landing mission and beyond, using reliable modular elements of existing, tested, and commissioned commercial space transportation assets. The LEADER mission is a phased evolutionary rehearsal to test the capabilities and performance of commercial space transportation systems, as well as lunar surface operation systems before attempting a much more complex activities. This mission proposes a plan to return crew to Mare Tranquillitatis region to explore the pits and conduct traverse to Apollo 11 site to survey the landing site in order to assess, protect, and preserve the historic sites and its contents. And the primary goal of this mission is to create a safe and efficient operational capabilities in the lunar habitation based during the early return of lunar exploration, while minimizing the use of EVA till the end of traverse operation. So within that, there are several rationales behind this concept. First, obviously, in a harsh lunar environment, safety is extremely important. This concept is a response to the key challenges involving astronaut safety during the lunar exploration. The challenges such as being exposed to lunar dust, radiation, temperature changes in EVA suits, landing zone safety, and ability to transport habitat modules. Second is the leader concept eliminates the need for astronauts to continuously transition between vehicles and reducing exposure to lunar extreme environment. And the third is that this mission is designed as a lunar daylight operation. And it's because a daylight mission is best for pilot and drivers for visibility, and it's very hard in polar region because of deep shadows and rough terrains, versus Tranquillitatis region provides smoother terrain and better landing access for both touchdown and liftoff. There are several principles involved within this mission. First, low Earth orbit integration and staging at ISS, enhancing safety through integrated design. Second, simplifying crew transfer EVA needs between transit, lunar lander, and surface vehicles. Third, providing instant mobility and flexibility upon lunar landing. And fourth, and most important part, is emphasizing on the economics and efficiency in lunar surface exploration. The journey to the moon begins with reliable and powerful launch vehicles. These vehicles will carry the components of leader mission to the orbit and to the lunar surface. The commercial launch systems such as Falcon 9, Falcon Heavy that can carry cargo and crew into the Earth orbit. It can also be used as a larger fairing and thrust pallets. So the thrust pallets are incorporating some components within. fully reusable propulsion systems specifically designed accommodating both the modular propulsion system and the leader lander rover assembly, control rupture airbag landing system, the very important aspect of the landing system, and fuel tanks. The thrust pilots are designed within two options. One with the base, which is going to be a base option, and second is going to be with a larger fairing with dragging capsule docked into the head of the rover within the thrust pilot. We're going to get back to the thrust pilot again, but first we're going to talk about the crew transfer. There are going to be 4 astronauts involved with this mission. 2 are going to be called orbiting crew. The orbiting crew will be sent within the precursory mission or operation to the lunar orbit to monitor the whole operation on the moon with the other two astronauts. There are going to be 4 astronauts involved. And also, the leader mission allows docking to ISS for a just to microgravity environment before the traverse at lunar surface. Back to the thrust pilots. So first, beginning with the base option, and that would require multiple launch vehicles. So there are going to be a launch vehicle to transfer transfer 2 crews to the lunar orbit for the precursory mission to prepare the operation, and the other 2 will be sent, and then the thrust pilot will be sent through the Falcon Heavy. The second option, however, is going to be a hybrid version of the thrust pilot. With a larger fairing, the Dragon capsule will be docked to the rover within the thrust pilot, and that will require lesser of the launch vehicles, and it's more efficient within the whole operation. So as we move forward to the landing operation and lunar surface operation, as you can see, there are two components that are very important: firing engine and control rupture airbag landing system incorporated into the design. So the descent happened with firing engine, and the airbag will be deployed upon approaching to the lunar surface, and an instant of mobility will be happening after touchdown and landing of the thrust pilot. The leader rover architecture will be incorporating all the components needed for the astronauts to have a living and working environment, and minimizing the need for them to come out of the vehicle with their EVA suits and have the operation, the traverse operation. And it's going to be a pressurized rover, incorporating, for example, the sample collecting box, manipulator arms, and so basically minimizing the need for them to come out of the vehicles. And one of the important aspects is that it has minimal amount of the windows incorporated to control the amount of radiation to come to impact the rover. The traverse operation, as you can see, starts from Mare Tranquillitatis pit towards the Apollo 11 touchdown within 4 days of the operation. And this is to develop and certify new technologies and mission operation as a rehearsal mission. And finally, as after successful completion of a traverse operation, at the Apollo 11 site, the crew will transition from their leader rover ascending to the dedicated ascent vehicle in their EVA suits and find their ways to the Earth. So as you can see, this last part of the last step of the mission is a challenge to the whole operation because we are requiring the astronauts to come out of the vehicle and find their uh, ascending vehicles. And that could be a future subject for this future studies. For the final note, it is important to mention that the LEADER mission is not just a strategic alternative. It is also a cost-effective approach in comparison to the initially planned Lunar South Pole mission. The use of already tested and operational systems reduces the financial burden associated with developing and verifying new technologies under the tight deadline. Thank you, everyone.
Thank you. Let's start video as well. Goes for those asking questions too. If you start your video, it feels a bit more personal with questions. Very nice presentation and well delivered. Let's see, we have one question here. Marufa,
Yes.
you're good at asking questions. Do you want to pop in yourself or shall I read?
I am.
I can, yeah, okay, go ahead.
Because I sit in these NASA conferences for a few days every week. So over there, you don't really turn on your videos. So this is very good to interact with the presenter.
Yeah.
So what are the timeline for this project? Thank you. That was a really great presentation. So I like your slides, the font and the design. You're welcome.
Thank you. So the intention is to it's a very conceptual mission architecture developed within the framework of the class. But the intention was to create this mission and have this operation before the actual Artemis mission, to use the already tested and commissioned systems to have a precursory mission, a test mission before the launching of the starships, for example, as a modular operation. If I answered your question.
No, I just want to know the numbers. Like for the is it an already existing project or is it a future project or?
No. No, it's just, as I say, it's just a very conceptual, very broad perspective.
To answer Marufa more precisely, I would say that this would be a mission that is quicker than whatever NASA's Artemis 3 is proposing, particularly because the vehicles are already existing. They are between 5 and 10 times cheaper than what Artemis and Orion can offer. And they have been certified. They are flying vehicles. So we think if Artemis 3 can fly in 2026, we can do this a year earlier, which would be next year. But the important thing to remember is that that particular rover design that Saba shows, we have to rework that some more. But those are things in the works as we talk, right, Saba?
Yes.
Thank you.
Yeah, it's a private mission, dear. It's not a. It has very little in terms of NASA NASA assets. Any more questions, guys? You got to ask questions. Come on, we need questions. Well,
No, I just commented actually. No, but it's the timeline is quicker than NASA.
that's right. That's the way to say it. That's exactly right.
Yeah, that makes sense.
And I
Yeah,
think
any more questions, please? This is an interesting concept. There should be questions for that.
Saba, do you want to show the picture of the model of the rover that we are building and testing?
Oh, yes.
There we go. And that is what a 6 to 8 person pressurized rover carrying unpressurized rovers would look like. And it would put the Lunar electric rover on the right to shame. I mean, that is a GM rover that you're seeing on the right side. The one on the left is the rover that we are studying now. The difference is massive, but we are looking at options for large pressurized rovers.
Yeah. Okay.
At the next, Nicholas, at the next LDC next year,
Yeah.
we'll have a far more detailed version of the large pressurized rover that
Sounds good. Sounds
operates
good.
using nuclear power. Yeah.
Yeah, work in progress. So there will be more detail next year. Sounds promising, I think.
Okay, good.
Yes. Okay. Any more questions? Otherwise, I think there come. Jason is good at asking questions as well. Do you want to pop in and ask the questions in chat in the video, Jason, or shall I read? Okay, he wants me to relay the question. So, what nuclear powered technology will the larger rover use?
Yeah, well, right now, Saba looked at kilopower, extending kilopower, and they have moved kilopower along quite a bit, but different kinds of cycles are being employed to increase the base load, to get up to 10, 20 kilowatts, but kilopower can handle 3 to 5 kilowatts, and that's plenty. That's plenty to keep it rolling.
Keep it rolling and keep the people in it happy.
I don't know about that part for now, but
that's important. Otherwise, they will become a danger. Have you been looking on the habitability of the rover, so to speak? Is it nice to live in, or is it just driving with you lean back a bit when you sleep? Or
well, I have some slides, but we'll have to wait a few more months.
Okay, that's for next year. Fair enough.
Yeah.
One more question here from Chris. What has your research shown about the feasibility of having externally mounted suits that the astronauts enter through the back rather than putting on suits inside and going out the general airlock? If you have been looking at that is.
Yeah, well, I think Chris may know that concept, and it was based on the Orlan spacesuits from Russia before it became what we call a suit port design, floated by Mark Cohen, and I've had several discussions with him about it, to the point of fist fights. But but I think there are some interesting thoughts about it. Maybe some of you can elaborate on it, but I think it needs a lot of work. Servicing, maintenance of spacesuits are all important parts that are difficult with the suit port design. But people have opinions. Hey,
Yeah.
this is the important thing about early design, right? We all have opinions.
Now there are coming questions. That's nice. Ibrahim Bey wonders if it is really necessary to design vehicles in point head shape in the absence of an atmosphere. Yeah, I guess they kind of look a bit aerodynamical.
Oh, I see. Yeah. Well, we have
Don't you
news
think
for
that the
you.
movable extra mass to change the center of mass within the vehicle help in landing?
There are two questions
No,
there.
that's two separate questions. Sorry. Yeah, let's start with the first one.
The first one is no. We have news for you, Ibrahim. There is no air on the moon to worry about aerodynamic aspects. And in terms of center of mass, it is a very good question. If you're moving at a considerable rate of speed, then you would consider really working the center of mass along the axis of translation. But all these rovers have difficulties moving quicker than 10 or 15 kilometers per hour. So we keep it on the ground and and don't move too fast. That is the strategy because on the moon, because of low gravity, driving on unimproved terrain quickly is not advised. You will lose traction, and then before you know it, you will lose control of your direction too. These are things that will need more study, Ibrahim. Good question.
Yeah. And if you have a quick question on the second
Yeah.
one, don't you think the movable extra mass to change the center of mass within the vehicle would help in control during the
Yeah.
landing, I guess
Yeah,
it is.
it will help. And again, these are things that are under study. One of the things in the flight of aircraft, they're constantly shifting fuel around to keep the center of mass and the CG aligned with the direction of flight. And this is also because of the moment of inertia, the dynamic moment of inertia. So those are things that we need to look at to see how to maintain a mass balance on the whole system. I'm thinking that now that AI is a tool that is available to us, there must be ways that we can settle that, Ibrahim. But you want to write a paper? Go for it.
Right. And we let that conclude the question for this. Thank